as people start to trickle back in, I will introduce our next speaker, who is Lisa Lendway. So Lisa has been teaching at Macalester College for the past 3 years. She teaches introductory statistics and data science courses and machine learning, and she is excited to debut an advanced data science and machine learning course next year. So before returning to Macalester, which she is an alumnus of, Lisa worked as a statistician / data scientist in a variety of industries, including retail, healthcare, and insurance. She strives to stay at the forefront of new R technology and to teach her students those skills so that they can thrive in the workplace or graduate school. When not nerding out about R, you can probably find Lisa biking with her spouse. She's super fit. Or spending time with her 8 and 10-year-old kids, or tending her large urban garden. She has like many tens of pounds of produce from her garden already this year. All right, so next up, Lisa Lendway, and the title of her talk is Reproducible Machine Learning with tidymodels. Take it away, Lisa.
Great. I'm gonna, of course, I lost the share screen button. Hold on a second here. Oh, not that one. Hold on. Okay. Can you all, okay, you can all probably see my screen. I can't see you anymore. Give me just a moment to straighten things out over here. I've lost my, oh, no, there that is. Okay. Give me one more second. Trying to see as many of you as possible. Okay. Here we go. And you can all see my presentation, is that right? Good. Yes. I see some nods and thumbs up. Excellent. Thank you, Christina, for that welcome. I forgot that I had mentioned my garden in that intro, and if you like that piece more than modeling, you get to see a couple photos of my garden, so yay. So I'm very excited to give this talk. I have to fully admit and disclose that I initially signed this up, or signed up to do this talk really for myself, because I wanted to learn more about tidymodels, and I thought what better way to learn about it than to prepare a talk and teach other people about it. So if you've done extensive modeling and love using the tidyverse, then I think this will be extremely exciting for you. But even if you've done just a little bit of those things, you should still learn something from this. And I'm going to go ahead, I have it listed up there, but if my copying and pasting skills can work, I'm going to go ahead and put this link to my GitHub repo in the chat. This is also on the North GitHub repo, but sort of mine is the one I'm keeping most up to date. So you can feel free to download or clone materials from there. If you want to follow along, I recommend using the tidymodels demo RMD file. It'll just be a lot nicer to look at than the slides. Okay, so in this talk, I'm really going to give a high-level overview of some tidymodels functions. So I like to think of this as a bird's eye view, right? In a couple cases, we'll get to see some detail, but that'll just be for the couple models that I'm going to use in our examples. But I'm hoping this is going to give you a little preview of what tidymodels has to offer, and it'll get you excited to go out and continue learning and exploring it on your own. So I know this font is probably kind of small for you, so I apologize for that. But we're going to walk through all of these machine learning steps using different tidymodels functions along the way. We'll start by using graphs to explore the data. That actually doesn't involve any tidymodels. We then split the data into different subsets. We pre-process that data, meaning we might execute some transformations of variables and other such things. Then we fit the model, which may involve tuning some parameters, and evaluate the model. Throughout the process, we'll question our model and think about consequences of using the model on new sets of data. All right, so to get started in the code, here's all the libraries that I'll be using throughout this demonstration. If you're following along in the RMD file, they'll be listed in the first code chunk. And I guess just to point out here, similar to tidyverse, if you're familiar with that, tidymodels is a collection of packages, which I've listed there. The data I'll be using is the house prices data set, or I should probably say one of the house prices data sets. This particular one is from the Modern Dive library. The data were originally from Kaggle. This data set contains house sale prices for King County, which includes Seattle. It includes homes sold between May 2014 and May 2015. So I'm going to start with some simple exploration of the data. I just want to caveat this with, I am not fully doing like a full data exploration that I probably would if I were really building a model, but I'm trying to sort of get through this quickly. So I'm doing a very basic exploration of the data. Here I've just looked at the distributions of various quantitative variables in the data set. So right away, some observations I make are, for example, we see that price is very right skewed, as are many of these square foot variables. We also see many zeros in some of the variables. So for example, square foot basement has a lot of observations with zeros in it, as does year renovated. That likely means that those homes don't have basements or don't have, or have never been renovated. So some things I might consider doing, I might log transform price and some of these square feet variables. I say that because I know I'm going to use linear regression to start. And with some of these variables that have a lot of zeros, I might consider just making them indicator variables, like has the house been renovated or not. Okay, then moving on to the few categorical variables we have. What I'm noticing here is some of these variables like condition and grade have very low representation in some of the levels. So for example, grade, there actually aren't any homes with a grade of 2. So in this case, I might consider combining some of these categories together. And I'll actually show you in a later piece of code that I do that. I also see that there's a lot of zip codes. So I'm sure I could do something interesting and useful with zip code, but I'm going to go ahead and just skip using that variable for now, at least in the model. The other variables we have are ID, which is just a unique identifier for each home. So that won't be used in the model. There's date of sale. I'm going to end up just using the month of sale as a variable in the model. And then there's another variable called waterfront, which just indicates if the home is on water or not. Okay, so before we jump into code, I just want us to have a nice overview of the modeling process. So we're going to start by dividing the data into training and testing. We use the training data set to fit different types of models and to tune parameters of those models if needed. The testing data set is saved for the very end to compare a small subset of models. In this case, I'm only going to show you 2 models, so we're going to apply both of those to the testing data. The training set is further sampled into smaller data sets. I'm going to go into a little bit more detail on this part later. Okay, so let's get into some of the code then. So we initially want to split the data into testing and training, and we're going to use a function called initial split. Good name, right? So 75% of the data will be assigned to the training data set. That's what this initial split function does. To actually access those data sets, you use the training and testing functions, and I've extracted them into house training and house testing. Later on, we're going to use something called five-fold cross-validation to further split up that training data set and to evaluate the model and tune the parameters. I'm going to go ahead and set up that data right now, and I'll talk about this more a little bit later, so that the data is split up using this v-fold CV function. And again, I'll explain in a little more detail what that's doing later. Okay, so this is a big, long set of code, and I've actually put it in here as an image because I couldn't find a nice way to put it all on here, fit it all on one slide. So I'm going to talk about the sort of each section of this code in just a moment. After the data are split, we use this recipe function to define the response or outcome variable and the predictor variables. And then we use a bunch of these step functions to pre-process or transform the variables. So now let's kind of dig into the different pieces of this code. So here's the very top of the code. So you see the recipe here. So again, this recipe defines the response or outcome variable and the predictor variable. So those of you who are familiar with the LM function, the variable to the left of the tilde is the response variable. Everything to the right is a predictor. Here I use the dot to mean all other variables in the data set. And then we get into the pre-processing or transformation steps. So step RM removes the variables that I've put in here. These are sort of redundant, so I'm getting rid of those. Step log takes the log of any variables I put in here. I've used some helper functions to help me choose those variables. And then continuing on to the next piece of the code, step mutate allows me to create my own variables in pretty much any way I might imagine. So for example, remember grade was one of those variables that had very little representation in many of its categories. So here I've made, if it's in 1 through 6, it's below average. If it's 10 through 13, it's high. And then everything else just keeps its number. Okay. All right, on to the very last piece of that code. Step date creates a month variable. In this case, you can see I've called out month there. You can do a variety of things. So like day is another option. Step dummy creates the indicator or dummy variables for categorical variables. So probably many of you who have used LM know that this typically happens in the background. Here we're doing that step up front. And then lastly, the update roles is used to change the role of some variables. So in this case, I don't actually want to use these 5 variables in my model. But I may want to use them in evaluating my model. So I've made up a role called evaluative, which means they're not going to be used as predictors. They're just going to be used to evaluate the model. Oops. Okay. So even though this step that I'm doing here is not actually necessary, I like to apply the recipe and steps to the training data just to check that everything went as planned. I'm the kind of person who likes to actually dig in and look at my data and play with it a little bit. So, oops. So a couple of things to point out. So notice that this variable is called square feet living. This is not actually square feet living, right? Most homes don't have 3 feet of square footage. This is actually now the log base 10 of square feet of living. So it keeps that same name even though I've transformed it. So just keep that in mind. And then we can see over here, same goes for price, right? So these houses are not $5. This is the log base 10 of price now. And then we can see over here some of these categorical variables that have been turned into indicator variables. There we go. And there's that date month variable I created, which is now also an indicator variable. Okay. Richard, I can get to your question a little bit later. Short answer is, in this scenario, I could use either bake or juice. Okay, so now that we have split the data and defined our outcome and predictor variables and the pre-processing steps, we're ready to model. So first we're gonna model price, which remember is now actually log-based 10 of price, using simple linear regression. So my hope is that this is a type of model that we're all familiar with. So in order to define our model, we need to do these steps. So we need to define a model type, which is the general type of model we want to fit. And again, I'm trying to copy and paste here. In this case, we use linear reg. I'm going to put a link in the chat to all the available functions in Parsnip. So Parsnip is part of the tidymodels set of packages. I believe it's a play on the package Carrot, which some of you might be familiar with. So yeah, go check that out. So first we define that model, again, linear reg in this case. Then we set our engine. The engine defines the package or function that we'll be using to fit the model. So in this case, it's LM. Then we set the mode with set mode. This is either regression if we have a quantitative response, or classification if we have a binary or categorical response. In this case, with LM, we can only have a quantitative response. We don't actually need this set mode piece, but I want to keep it here so that we don't forget about it later, because I don't know about you, but I'm pretty good at forgetting those little things. There is also an optional set arguments piece, which I'm going to show you later. That's if we have arguments that need to be tuned, which in this case we don't. Okay, and then just to point out, this is merely setting up this process. We haven't fit the model to data yet, and there's still one more step we need to do. That is creating a workflow. So the last step before actually fitting the model is setting up a workflow. This combines the recipe and steps with the model. So you can see we start the workflow, we add the recipe that we created earlier, and then we add our model. So now we have, like, I guess all the ingredients, right? I'm trying to make analogies on the fly. Okay, and then this is our workflow output. So again, there's nothing has been fit yet. This is just telling us, like, here's all the things that we're planning to do. All right, now we're finally ready to fit the model. So after all that work, this part actually seems really easy. So we use the fit function to fit the model. So we've taken this workflow and are feeding it into this fit function. And we're going to fit the model on the training data set. And then I use this pull workflow fit and tidy function to display the model output. So this should look like sort of fairly standard linear model output. Okay, now, usually after we fit a model, we want to evaluate the model. So I know probably a lot of you have used k-fold cross-validation before, but for those of you who haven't, I don't want you to feel left out. So I am going to take some time to give a brief overview of what it is. So if we want to know how well the model will perform on data it hasn't seen before, we can use this k-fold cross-validation to do it. In k-fold cross-validation, we divide the data randomly into k approximately equal groups or folds. This schematic here shows 5-fold cross-validation, which is what we're going to use on our data as well. So the model is fit on k-1 of the folds, and the remaining folds is used to evaluate the model. So if we look at this first row, this represents the model being fit on folds 2 through 5, and then being evaluated on fold 1. RMSE, root mean squared error, is a common performance metric for models with a quantitative response. So it's computed by taking the difference between the predicted and actual response for each observation, squaring it, and taking the square root of the average over all observations. So again, looking at the first row, the model is fit on folds 2 through 5, and then we compute the RMSE on the fold 1 data using the model that was fit there. If we look at the second row, the model is fit on folds 1, 3, 4, and 5, and then we use that model to compute the RMSE for the data in fold 2. And after this is done for all 5 folds, we take the average RMSE to obtain the overall performance. This overall error is sometimes called the CV error, or cross-validation error. And averaging the performance over those K folds gives a better estimate of the true error than using one holdout set. It also allows us to estimate its variability. Okay, so this might seem like a lot of work, but thankfully this is super easy to implement with the fit resamples function. So here's that code. So we again feed in the workflow. We use the fit resamples function with that cross-validated data I made earlier. And then we can look at some of our metrics here. So this column called estimate shows the RMSE for each fold. You can see that they're similar, but not all the same. And then here, oops, shoot. Oh no, hold on a second. Did that wrong. There we go. Okay, then the collect metrics function averages these metrics over all the evaluation folds. I also provided the code to show you how you could do that by hand so that you know where it came from. In this simple scenario, we might be interested in seeing how the model performs on the testing data that was left out. The last fit function will fit the model to the training data and apply it to the testing data. Because it's using the workflow, it is applying the same transformation steps to the those step functions to the testing data as were applied to the training data. And then after the model is fit and applied, we can collect the performance metrics and display them and show a sample of predictions from the testing data. Okay, so collect metric shows the results applied to the testing data, and then here's the predictions on the testing data. Okay, and like I mentioned at the very beginning, this shows predicted versus actual prices for a zoomed in subset of the data. It's important for us to think about how our model is going to be used and specifically how our model could do harm. So this isn't something maybe as machine learning folks we always think about, but we should. So I'm doing a very simple thing here. But one thing I'm noticing right away is that the lower priced homes are on average overestimated, whereas higher priced homes are on average underestimated. So if this model was used to, let's say, determine the price of homes for property tax purposes, this could be pretty bad because people living in lower priced homes would sort of pay more than they should, and people in higher priced homes would pay less than they should. So just one quick way I can sort of evaluate my model. So I wouldn't want to use this model for that purpose. I'd want to improve it more before doing that. Okay, for some reason I seem to be talking a lot slower than I did when I practiced. So I'm going to try to just point out a couple of, you can look through all of these materials in my the online link I showed you. I just want to show you here, if we had a model that we needed to tune a parameter, so like lasso, not a whole lot changes. One thing is we need to add this set args function. Here, the argument that I'm trying to optimize is this penalty term if you're not familiar with lasso, this method shrinks some of the coefficients to 0 based on a penalty term. So I'm telling it now that I'm going to tune that penalty term. I create the workflow much as before. This just shows that, yes, I've updated that workflow. And then the part that's different is I need to tune this penalty term. So first I have to choose my grid of penalty terms I want to try. There's functions here that can help you do that. Then I need to use this tune grid function. So this is different than what we did before. This is an extra step where I'm going to now evaluate all these different tuning parameters. I do this using cross-validation, similar to what I did before to evaluate my regular linear regression model. And again, I'm going to skip through some of this detail, but you can see that it is doing this on all the folds. I've shown you an example here. And let's see, I can find my best tuning parameter. And there's just a visual of it. And once I have that best parameter, I can use this finalize workflow function so that it uses that parameter. And then I can refit my model using that parameter. So this will fit it to the training data and apply it to the testing data. And I've collected those metrics here. So a little bit changes, but it's not too difficult. And I am going to give a quick thank you to all these folks who have provided some really great resources. I would highly recommend checking those out. I used a lot of their materials to build these slides. And I want to thank all of you for being such a great audience. And I wish you the best in your tidymodels endeavors. And is there time for questions?
Yeah, we've got a couple minutes for questions, and we did get one, which was, I'd love to hear your thoughts on this tidyverse approach versus base R for machine learning. Some of these functions, while cute, seem a bit more opaque in terms of what they're doing. Would you use this again? Do you think it obscures the steps too much to teach students with it?
Sure, that's a great question. So my thoughts on that right now would be, like, I wouldn't use this in my intro stats class, partially because I'm also not familiar enough with this stuff yet to use it at that level. I would definitely use it in machine learning. I think there's a lot of things that are more clear doing it this way than they are, like right now I use carrot, and not that I don't like carrot, but I think this just cleans things up a lot. I also happen to love the tidyverse. So for me, this just kind of the flow of everything is better. And actually, just to comment on one other thing about obscuring the steps, I actually think it's just the opposite, because I think it's like really clear. Now you have to sort of understand a little bit about why it's doing it, but you know, the fact that I'm telling it like use engine, set engine is the function, LM, it's like I have to call that out specifically, whereas like to compare it to carrot, I felt like sometimes some of that stuff was more hidden.
Cool, thanks. And then we have like 1 minute left, so we'll get your real quick opinion on this. How would you compare this to like scikit in Python?
Yeah, I don't use Python. Oops, sorry, car going by. I don't use Python, so I can't at all compare that. So sorry.
Perfect. Nice short answer. Fits in the time. All right, well, we have 5 minutes of a break, and then we'll get on to our next talk. So go take a quick stand up and stretch break, and then we'll be right back. Thank you so much, Lisa.
You're welcome.